And I'm pleased now to introduce the first of the research papers at ISMM this year. This is continuing the topic of processing and memory. And the speaker is going to be Morimoto, talking about Gray and Young, a generational garbage collection for processing and memory.
Good morning. I'm Morimoto from the University of Tokyo in Japan. Today I'm going to present our work titled Gray and Young, a generational garbage collection for processing memory. As mentioned in the keynote by Professor Kim, processing memory referred PIM is attracting attention. A key feature of this approach is that computation is performed where the data resides. Please take a look at this figure. In a conventional architecture, the CPU and memory are connected through a memory bus. To perform computation, data is repeatedly transferred between the CPU and memory over the bus. In memory-intensive application, a massive data is transferred, which becomes a performance bottleneck. In contrast, the PIM approach places a processor near the memory, and the processors process data there. This approach is expected to solve the bottleneck caused by the massive data transfer between the CPU and the memory. UPMEM PIM was a publicly available PIM device. In a UPMEM PIM system, computations are performed on UPMEM PIM-enabled memory. The structure of this memory is shown here. DRAM Processing Unit, or DPUs, are in the DRAM chips. And each DPU has its own instruction RAM for storing the binary for DPU and scratchpad memory. DPUs access DRAM through DMA. In this research, we developed an efficient garbage collection for virtual machines running in a single DPU. There are two challenges. The first challenge is that fine-grained DRAM accesses are slow. Therefore, in garbage collection, small DRAM accesses such as pointer-sized loads or stores should be minimized. The DPU accesses scratchpad memory in one cycle. However, it accesses DRAM through DMA. This graph shows the throughput of DMA. The higher the better. As you can see, throughput with small DMA size is very low. According to an experimentation done by another group, a single DMA transfer spends at least 70 cycles. With large DMA sizes, overhead of DMA transfer is alleviated. The second challenge is that the instruction RAM is very small, only 24 kilobytes. Because of this, we must reduce the binary size so that the binary fits within the instruction RAM. Here are our contributions in this work. We have developed a generational garbage collection for DPUs. This garbage collection is designed to reduce DRAM accesses through DMA in minor collections. Moreover, we designed the garbage collection to keep the binary size small. This is an overview of our garbage collection designed for DPUs. We place the young generation in the scratchpad memory and the old generation in DRAM. The class table is also placed in DRAM. Minor collection runs in parallel, and we apply two techniques to reduce DRAM accesses. Major collection is a more compact garbage collection. Currently, it is a single-threaded. Parallelization is left as future work. In the rest of the talk, I will mainly focus on these techniques. So let's look at how DRAM accesses occur during a minor collection in an ordinary algorithm. Here, we focus on this orange object. First, the object is copied to the old generation. This W mark indicates our write access. Because this copy is done with a single DMA, I put a single W mark here. Next, we access the class table to know which fields in the object are pointers. So I put our R mark for reads. In this example, we can see that two fields have pointers. Then we read these fields to traverse the child object, so I put two R marks for these. Later, each child object is also moved to old generation, and here we assume they have been moved as shown. Finally, we update the pointer field of this orange object to point to the new location of the child object, so I put two W marks. As you can see, this process involves many reads and writes to DRAM. This is because the object is accessed for traversal and pointer updates after it is copied to DRAM. In other words, the object is copied while it is gray in trickle abstraction. To reduce these DRAM accesses, we propose to keep objects in the young space while they are gray. In this method, reading and updating pointers are performed on the scratchpad memory, not on DRAM. After all pointers have been updated, the object is moved to DRAM. The object is moved to DRAM in a single DMA operation. I will explain details of this algorithm with this example. A is pointed to from the root set, so A must eventually be moved to the old space. Unlike the ordinary algorithm, we do not immediately copy A to the old space. Instead, we reserve space to which A will be copied and install forwarding pointer to A. Then we scan A in the young space for its children. In this scan, we find C and B. We move them to the old space in the depth first order. For C, we reserve its destination and then scan it. Now we find a pointer to A, which we have already visited. Since A has a forwarding pointer to its destination, we can update the pointer in C. Once all the pointers in C have been updated, we copy C to the old space with a single DMA. We move B to the end space. We move B to the old space in the same way. Now all the children of A has been moved. We updated pointers A in the young space and copied to the old space. First, we update pointers A in the young space. Then finally, we copy A to the old space. Next, we focus on these accesses to the class table in minor correction. For each live object, the corrector reads the object layout information, or OLI, from the class table, which is stored in DRAM. Because this access happens once for every live object, it results in a large number of DRAM accesses. To reduce these accesses, we take advantage of the characteristic of the virtual machines assumed by our garbage collection. Our garbage collection is designed for the Java framework for UPMEM PIM. In this framework, Java methods can be offloaded to DPUs. For each method that can be offloaded, the framework prepares a dedicated binary for the DPU. We refer to such method as kernel method. An important characteristic of the UPMEM system is that when a new binary starts execution on the DPU, the contents of the scratchpad memory are cleared. In contrast, DRAM contents are preserved across multiple binary execution. Therefore, we move all live objects to the old space and empty the young space when kernel methods are complete. So, our second proposal is to cache object layout information in scratchpad memory. To take advantage of the property of the system, we make an optimized image of cache for each DPU binary. As we see in the previous page, we empty young space when a kernel method is complete. In this figure, when insert method is completed, young space becomes empty. And then the next kernel method starts with an empty young space. As a result, all objects subject to minor correction were created with the currently running kernel method. Based on this observation, we prepare optimize cache image of OLIs for each method in advance. When the method starts execution, the corresponding OLI cache image is loaded into the scratchpad memory. Finally, to address the limited size of instruction RAM, we propose separating the major correction binary. In this approach, as shown here, only the minor correction is linked to the computation kernel that runs on the DPU. The major correction code is excluded from the computation kernel. When a major correction is needed, a separate binary containing only the major correction is executed on the DPU. With this separation, we reduce the size of the computation kernel by approximately 6.9 kilobyte. This design also has an important advantage. Since the major correction is isolated in its own binary, we can allow its code size to grow in the future. For example, if we improve its performance or implement more complex logic. To evaluate the performance of our proposed garbage collection, we developed a micro benchmark. This benchmark repeatedly creates a binary tree by inserting elements. Once the number of elements in the tree reaches a certain threshold, denoted as alpha, the tree is replaced with an empty one. As alpha increases, more objects survive in the young generation and get promoted to the old generation in minor correction. This graph shows the total time spent on minor correction. The lower the better. For each value of alpha, we applied our proposed techniques, gray in young and OLI caching. Across all alpha values, we observe consistent speed up when applying these techniques. At alpha equals 100, applying the gray in young techniques alone resulted in 31.5% speed up. Adding OLI caching further improved the performance, reaching a 46.2% reduction in garbage collection time. To understand the cause of this improvement, we analyzed the DRAM accesses in minor correction. The left graph shows the number of DRAM accesses, and the right graph shows the total number of bytes transferred. The lower the better. In both graphs, we can see that our proposed techniques significantly reduce DRAM accesses during minor correction. At alpha equals 100, gray and young alone reduce the number of DRAM accesses by 36.3%. With class table caching also applied, the reduction reaches 85.9%. These reductions contribute to the improvement in minor correction time that we saw earlier. This chart shows the scalability of our parallelized minor correction. The lower the better. As we increase the number of threads, the garbage collection becomes faster. We observe the highest throughput when using 11 threads. However, for small alpha values such as 7 and 15, the throughput is saturated at fewer threads. This is because when alpha is small, there are fewer objects promoted from young to old generation, which means less work that can be shared across threads. Let me briefly introduce related works. Generational garbage collection that places the young generation in the scratchpad memory has been studied in prior work. This work mainly proposed a pre-tunneling algorithm. Unlike our work, they also place long-lived frequent accessed objects, so-called hot matcher objects, in the scratchpad memory. Another line of work focuses on identifying pointer field during object scanning. While our GC, our garbage collection, simply reads object length information from the class table, there exist several prior studies that propose optimized techniques for object scanning. This is summary. Thank you.
We have time for a few questions.
How difficult would it be to do a benchmark, a real benchmark to run on this?
Okay. So in my work, benchmark is only one seat, and the difficulty of making benchmark is that first one is yes, instruction RAM is very limited size, and second that benchmark for this DPU UPMEM PIM is not there are no suitable benchmark for DPU. So yes, these 2 points yes, that is difficulty.
So the question is that I know you look at the class information to know the object layout to find the pointers, but this is only one way to find the pointer. There are also alternatives. Such as one example is that you put a small bitmap in the object right in the object header, so that you no longer need to look at the class information. Have you considered this method, and what do you think the impact of this would be?
Yes, that is one way of identifying the pointer. And so if object the header contains bitmaps, so if bitmap is 8 bytes, each object increases the size of object header, so the heap is more more and more minor collection, garbage collection is more time triggered because the heap will be soon full. So yes, but yes, as I mentioned in related work, that is one way, and we don't apply the optimization for identifying pointer.
Maybe one last question.
So thank you for I have a question about the latency factor. So as I understood, I guess you measure your throughput only for a single kernel execution. And I guess the minor garbage collection between across kernel executions may enable latency. So do you have any insights?
Thank you for question. So yes, if the as our future works, if the latency sensitive application, like incremental ZC garbage collection is one of the way to reduce latency. But now our garbage collection is stop the word garbage collection, so latency is yes, if the GC is occurred, the latency is not latency is high. So yes.